Hi, this is Dr. Pingle here with a lecture on raster and vector conversions. We're going to break this into several parts. This is part one, simple gridding with feature to raster. So I'm going to begin this with a story. So when I was a kid, I was really into reptiles. I had a little book that you see there at the left. That was actually the very book that I had, Golden Nature Guide, Reptiles and Amphibians. And I would just kind of pour through this thing and see what kind of lizards and snakes and turtles were in my local area. And in that map, or in that book rather, they had these maps that would give these species distributions. And so this isn't one from that book, but it's similar. So this is the species distribution map that I pulled actually from Wikipedia for the timber rattlesnake. I really thought it would be. I grew up in eastern Iowa. I thought it would be really cool if we could find a real poisonous snake. And so the timber rattler was the one that I had heard from my friends that might be around. And so I looked it up and it looked something like that. So I would kind of pore over these maps. And, when I was a kid, 6, 7, 8, I didn't really know, map reading was a little tricky. So I would kind of look over this and try to figure out exactly where I was. And this is sort of, before Google Earth and so it was a little more challenging than probably it was than it is today. But I would sit there and try and pretend that I think I'm right on this line. I think maybe there are timber rattlesnakes here. This map that I had pulled in actually comes from Wikipedia. And where did Wikipedia get it? Well, it was produced based on the IUCN, the International Union for Conservation of Nature, Red List of Threatened Species, and so I thought this was pretty cool. A lot of times, one of the great things about Wikipedia these days is that a lot of the sources are pretty well documented. So whether it's a map or an image, you can usually track down the original author. If you go to the IUCN Red List of Threatened Species, you'll get a page that looks something like this. And what you can do very awesomely is you can create maps, species distribution maps, based on the information that they have. You can browse all of these pretty easily. So this is the timber rattlesnake again. This is the species distribution map. So you can browse and pan and do all the normal things that you're used to doing with a web map. But if you create an account there, which is free, you can download the original data. So if you are a GIS student that's studying biology or environmental science, you may be interested in some of that data for a class project. So I pulled the data down and brought it into ArcGIS and took a look at it and mapped out whether or not the region for timber rattlesnakes was actually in my hometown or not. So I'm from Ely, Iowa, and sure enough, timber rattlesnakes show up as being included in that species distribution. So that was great. But DeKalb doesn't. DeKalb's not in there. If we measured, we would find out that DeKalb to the closest distance is about 16 miles or so. So that's very exciting. Sort of have this idea of Indiana Jones and the pit and Raiders of the Lost Ark with millions of snakes all around. Probably more fun for me than maybe some of you. But obviously this isn't quite right. There's something wrong with that conceptualization. It isn't as if we can just go 16 miles and we walk right into snake country. And I think people kind of intuitively understand that. But this is a good chance to sort of think a little bit about more deeply how GIS data can often be misread, how you need to sort of take into account those differences in data to really get the right answer. So that's what we're going to focus on a little bit today. So we need to think about a little bit what's going on with the issue conceptually. What's wrong with things like species distribution maps? Obviously, we have them for a reason. They're a simple presentation of where you might find that species. But clearly, there's some uncertainty. There's some gray areas on the boundary lines. And even within the boundary, your likelihood of encountering this species or that species definitely varies. So how do we accommodate that digitally? How do we include that as part of our analysis? This practice actually is a feature called redlining. Redlining we'll talk about here on the next slide here, but the gist is that we're using sort of these hard boundaries where none exist. And a really common example is something like this one. So take a second and look at this map. So this is a map of crocodilians per country. I don't even remember where I grabbed this one. But it's color-coded, so certainly we can talk a little bit about the appropriateness of that color scheme. It's not terrible, but probably something like a unipolar scheme that goes from light to dark of one given color would be a little bit better. But that's not really the big problem here. The big problem is that we're mapping these things on administrative boundaries. And for a choropleth map, certainly crocodilians are not, they don't care whether they're in Brazil or Peru or Bolivia. They really, they're paying attention to their environment, and they don't care anything about administrative boundaries. So using a choropleth map, something where administrative boundaries are how things work, is usually not a good idea for natural phenomenon. It's sort of, people like it. They can identify country boundaries, and so people are into that sometimes. But generally speaking, a bad idea. So redlining itself actually gets its name. It's a relatively recent phenomenon. So this is something that came to light in sort of the middle of the 20th century. And what it was a practice of denying or charging more for services in a particular area. And so the idea here is that a banker, somebody with investment money, would sit down with a map, and they'd sort of draw these lines on the map indicating what were the sort of good areas, what were the bad areas to invest in. Bad areas you would charge extra in terms of interest rates, or you may not grant loans at all. And so the story is that they would, back then, color printing was not widespread, and so they'd have these black and white maps, and so they'd take a red marker and they'd mark sort of the good or bad areas on that. So down below is sort of a modern incarnation of a redlining. This was, kind of a rough practice. This, definitely some structural racism going on here, and so it's kind of a bit of a dark spot in the history of mapping in GIS. If you're interested in this topic, there's a lot of really good resources. There are a lot of really good books on the subject. If you're interested in some of the original data, I provided a couple links here for you. So if there are history students in the audience, you may be interested in that. So we're kind of talking about redlining more by analogy than anything else. This isn't real redlining, but again, we're using essentially a digital marker to mark where species are and where they aren't. Maybe we have a third category. This particular map is a map of king mackerel. So we've got the legend here indicates sort of a dark red for certain, hashed lines for not certain, and certainly the fish don't really respect these boundaries, right? So it's a little, I don't know why, but it strikes me as even sillier than normal to draw these hard lines in an ocean where clearly there are no boundaries at all. There are other ways to approach things like species distribution, and this is an interesting example of one. So this is the Early Detection and Distribution Mapping System, and it's an example of volunteered geographic information. So VGI is a relatively new phenomenon. It kind of comes out of the same sort of spirit as what gave us Wikipedia. The idea is that you've got a public that might be interested as a hobby. They might be carrying things like cell phones around and can sort of add or log data as they go. And so people will volunteer, people will contribute this information for free. And so you're crowdsourcing this data, you're getting the public to participate. This particular system is still really new, not particularly well used. And so when I was looking for some of this stuff, I pulled this one up. This is a map showing the distribution of the Texas horned lizard. Clearly something is going on here, and what's going on is that there hasn't been enough volunteered geographic information to really make this work. So OpenStreetMap is a really great example of volunteered geographic information, a lot of people contributing this stuff for free. Unfortunately, even OSM is pretty uneven. So some places, when somebody gets really interested, might have a lot of information. But in other places, there may not be very much information. County level data can help sort of mitigate this problem a little bit. So if you turn on the county level data for this one, you can sort of see, different particular spots. We still have a problem though, right? Going in at a finer scale doesn't really solve the problem. It just maybe makes things a little more apparent what's going on. You can actually pull up on this website the point data. So people have contributed information about this. And this is what it sort of looks like in its raw format. So this is an Excel-based document that includes latitude and longitude as one of the columns. Some extra information, obviously the species that we were interested in. But this is what the data looks like. It's all point data, right? It's all individual observations. And maybe they saw one or more things, but it's all at one given latitude and longitude, right? It's not an area. It's a particular point. So one way that you can really get a handle on looking at this stuff is to just map those points. So rather than showing a choropleth map of the Texas horned lizard and seeing that it's only in Florida, which doesn't really make a lot of sense, we could just pull up all of the dots, and whoever contributed things, we can see where that was. This is not going to really solve our problem, but it's not a bad first step. So we would consider this as a good idea for exploratory data analysis. So exploratory data analysis in GIS is going to be sort of pulling up the data, looking for patterns, but this is the step where you're sort of looking for connections, rapidly moving through and visualizing the data. You're not really trying to make a case. You're not doing what's called confirmatory data analysis, where you're running statistics to try to see whether or not there's a statistically significant difference between results. No, this is just sort of like looking for general patterns, so it's an earlier stage of analysis. One of the problems that you get with something like this is that dots can overlay, and it can be very difficult to see what happens when those dots get extremely dense. So this is a map of the DeKalb area, and I pulled in dots that represent the position of buses as they move through the Husky bus system. So you can see different points, these different latitude and longitude at given, these are all at separate times. So every, let's say 10 seconds, the bus rings in and says, this is where I am at this point. And this collection took place over a couple of days. And you can start to see the outline of where all the buses go, what's more common, what's less common. So for instance, you can see along Peace Road over here, it's relatively less dense. But once you get onto the university campus, we've got a bus loop over here. This is the Holmes Student Center. These dots are sort of piled on top of each other, right? Lots and lots and lots of dots in this area as the buses are stopped, as more buses move through. This problem, by the way, is not unique to geography. This is very common. And so what we want to do is hook into existing wisdom and scholarship on this topic. So what we'll talk about next here is a little bit about statistics. And statistics is sort of one of the kind of cross-disciplinary languages in all science and engineering. So let's take a look. Usually what we do with point data is we visualize these things in a couple of common ways. So one is a histogram and one is a box plot. So what a histogram is going to do is it's going to create these bins in our data, like you see at the left. And then we just count or calculate the frequency of the number of observations that fall in that bin. So you usually see this sort of thing like a bell curve kind of thing emerging. And you can do the same sort of thing with a box plot. So at right we have a box plot. These are a little less common, but they show you usually the interquartile range. So what's the 25th percentile, what's the 75th percentile. They'll show you the median. So usually that, in this case, that's where in these boxes the line is drawn inside the horizontal line. And then it'll show you the outliers, so the extremes of your data. So we have some idea of what the bulk of our data is like, but we also have some idea of what the extremes of our data is like. The histogram itself is really not unlike a choropleth map. So in a choropleth map, we have similar sort of spatial extents. They're not even, But essentially what we do is we're defining a boundary, a bin, much like we do over here on the left. And then we just count how many things are in that bin. We may calculate other things like the mean for that. We may count total population. But it's really not all that much different. And even when we're rendering this stuff, we're using systems like we see on the lower left and lower right rather of the legend. We're dividing these things into bins of equal width, and we're just we're color coding these according to the number. By the way, good chance to sort of inspect map making. So this is just kind of a common example that I pulled somewhere off the internet. But you'll notice that we're missing things like commas as thousand separators, which makes this a little bit difficult to read. There have been some examples in the literature of histograms that don't work quite this way. So instead of having bins that are equal widths, these bins are unequal widths, and so you will see that once in a while, but that's pretty rare. The width is something that is sort of the choice of the person that's doing the graphing, or if you're making a map, the mapping. So the width, the size of the bins is called the bandwidth or the bin width, and you can change this up. So this is an example of what the same data looks like. On the left, we're using 10 bins to do it. On the right, we're using 20 bins to do it, so the bins are half as wide as they are on the left. Another technique that we use to take a look at point data is the scatter plot. So this is where we might plot one kind of point data against another. This is some Python code that I use to just make a quick scatter plot. But this is really not that much different than something like a species distribution, right? So as we, let's say we send out 10 or 20 volunteers and they're out kind of combing the area, and what they're trying to do is they're trying to count how many whatevers, timber rattlesnakes or whatever they are, how many they see. And so this is the kind of data that you might get back if you sent those people out into the field to collect data like that. So the question is, how do we turn this into a better visualization, a more appropriate visualization? So the 2D histogram is one way to take point data and turn it into a raster. So if we sent those volunteers out into the field and we collected where they saw those things, maybe it looks something like this. And so one thing that we can do is we can overlay a grid and we can just count how many dots fell into each grid. So that's what you see down at the bottom. This is a representation of the grid and how many dots fell into each grid cell. So in this case, many dots fell into this cell right here. Quite a few fell here, and then they kind of go out so that if there were 0 dots, then we colored it blue. And this might be a little deceptive when you look at the scatter plot. You may not notice, you may not immediately pick out that one cell that had the most number of dots. But the reason for that is that these dots can kind of wind up one on top of the other. And so this is why you have to be very careful when looking at dot density data, that you're not looking at data that's just sort of been overlaid. The way that you do this within ArcGIS is using the feature to raster tool. So this is located in conversion tools, but of course you can always just search for it. So the feature to raster tool's job is to take these often points, but you can actually use lines as well. Usually take these points and to turn them into a raster. So this is an example of what that might have looked like using the Husky bus tracker data. We have all these buses running on the system, but the different buses have different lines. So maybe it's the 11 or the 2L or whatever they are. And so what we want to do, in this case, we've got them colored by that route. And what we want to do is we want to create a histogram based on that data, a 2D histogram. So the feature to raster tool looks something like this. This is a screen grab of some of the info I got from Esri. The gist is that it's going to convert features to a raster data set. It'll work on anything, so point, line, or polygon. If you want some more specific options, so if you're really kind of getting into the details of how this tool works, you may want to look at the specific tools, point to raster, polyline to raster, and polygon to raster. They're essentially going to do the same things. They'll just allow you to have just a little bit more control. So the idea is you're going to take some kind of an input vector data set. It doesn't really matter the format, geodatabase, shapefile, and you're going to spit out this raster image. As I said, things like point to raster, the specific tools are going to be allow a little bit more specialized operations. And one of the really important ones here is the cell assignment type. So this is the cell assignment type, again, one of the most important features. Cell assignment type is going to be the way that when you draw that grid on the points, how do you decide what value it should be? And you can imagine that if you've got a number of different points in there, you've got to make some decision about, well, what grid value do I want to give it? So sometimes what you want to do is a count. So maybe you saw 11 rattlesnakes there. You want the number for that grid cell to be 11. But maybe when you were out in the field, what you did was you measured the length of those rattlesnakes. And so you have 11 different measurements. Well, you don't want to just add all of them up, right? You don't want to count the length of 11 snakes laid end to end, although potentially you might want to do that for some reason. More likely what you would want to do is you would want to calculate things like the mean, or the maximum, or the minimum, or the range, or something like that. So those are very common. You can actually use the sum if you're interested in that, and there may be a good reason to do that. The last one, though, is also very important. So that's the most frequent. So here, what you might want to do is if you had things that were nominal classes, so they weren't numbers, but maybe you wanted to count, maybe you were sent out and you were supposed to count all of the snakes that you saw, and you were recording the species type. So you saw 11 garter snakes and 8 timber rattlesnakes and 9 king cobras. Well, what do you want to do with this? Well, maybe what you want to do is draw the picture, count that pixel as whatever there was the most of, and so it would look at those and it would see which one you had the most, and it would record the value that way. So the cell assignment type in combination with the value field is what you're using to count, so it's species type or its length or population or whatever it is that's in the attribute table that you're interested in using to calculate these numbers. So these are really important things to know. So we'll talk about this a little bit more at some point, but you really should have a good idea of how these different cell assignment types are going to yield different values based on how you use them. This is an example submitted by a former student in this class who created a map of dominant crime by majority pixel classification. And so the idea here was we got a data set, which was a point data set where all of these different crimes occurred. So we had a latitude, longitude, and the type of crime. And so essentially what the student did was to grid those values and then to create a most frequent classification to figure out what kind of crime was the most common in that particular grid cell. So it was a really interesting project. So you can see that New York, it's zoomed in a little bit. LA is quite a bit more spread out, so it's a little harder to tell. But in New York, you can see that most of the crime is larceny, theft. You see these big tracts of red, which are burglary. But you can also see little tiny places where certain kinds of unusual crime are more common. So you can pick out a couple of little spots where grand theft auto is the most common. So a very interesting way of looking at what would ordinarily be a pretty chaotic data set. One of the things that you can do is you can define the cell size. So when you're doing this, you need to decide how big those squares, how big your grid is going to be. So this is one of the ways that you can do that. It'll calculate one kind of by default. It'll usually try to divide these up into 250 by 250 pixels, but you may not want to do that, and so you might want to specify a cell size of 100 meters or 1 kilometer or whatever it is that you're interested in. So this is essentially, this is what that data might look like applied to that Husky bus tracker data. So we take all the point data of the observations of where all the buses were. And we might use something like count. So how many buses did we see in that grid cell over that time period? And this is essentially a 2D histogram of the data set to kind of bring this around full circle. So this is a map showing where buses are the densest, where the buses are most frequent. And so you can see that around campus over there on the left side of this is the most common. But you can pick out a couple of other spots. I think on the right you see these single points where buses tend to be parked or stopped for an extended period of time. But this is a really good way to analyze things like the coverage on a bus network. So which places are served most commonly. This is one easy way to make those calculations. And one final piece here, I wanted to talk about projections and 2D histograms. So when you're making these counts, one of the things that you want to be aware of is that your grid cells are all of equal size. So the easiest way to do that is to project your data into something local, so state plane coordinate system or UTM, something like that. If you just use latitude and longitude, keep in mind that since the lines of longitude converge at the poles, there's a difference between the length of 1 degree at the equator of latitude and longitude, where those are relatively equal. Well, by the time you move northward and you get to the North Pole, 1 degree of latitude is almost the same as it was, but 1 degree of longitude is much, much smaller in terms of real distance on the ground. So it's almost never a good idea to do this gridding by latitude and longitude. You're almost always going to want to project this into some other reference frame. So there's a quick introduction to some of the issues involved with featured raster. We'll get into some of the more complex topics next time. But thanks for listening, and we'll see you next time.